Namaskara. We were looking at the ways in which we can take advantage over the divide and conquer paradigm. The naive application of divide and conquer paradigm may or may not give a best possible solution. So, after designing a divide and conquer algorithm, we need to explore the possibilities of improving them. Towards that, we have already observed certain strategies. In the case studies for finding the max and min, we have found out that bottoming out earlier helps to speed up a divide and conquer algorithm. Also, by dividing in a clever manner, we can gain some more efficiency. And then we have seen a very interesting paradigm called more for less, and this idea is going to be applicable is going to be applied for the divide and conquer algorithm. Towards this, we have seen the case study on maximum subarray sum problem. You are given an array A 1 dot dot n of n integers. They can be positive, negative, 0, multiple copies, it is arbitrary. A subarray sum Sij is defined as sum over k running from I to j of ak. A subarray is defined by a pair of integers I and j, I less than or equal to j, and a subarray sum is sum of all the elements found in that subarray. We are interested in finding the maximum subarray sum. So, maximum subarray sum is maximum over all such subarray sums Sij, 1 less than or equal to I, less than or equal to j, less than or equal. We have already discussed a divide and conquer algorithm. The complexity of the divide and conquer algorithm, okay, the direct divide and conquer algorithm has complexity order n log n. It has a complexity n log n. So, for a given array A, we split into two parts, A 1 dot n by 2 and then we have found out the maximum subarray sum of this part and maximum subarray sum of this one, and in order to combine the solutions you have to do lot of work, and then you have found out the maximum subarray sum. You have used them and then you have found out overlapping sum. Now we are going to change our specification. So, given an array A 1 dot dot n, I am going to demand more. In addition to the maximum subarray sum, I want some more values to be output by the algorithm. Okay? So, we will now give the specifications for those values. Normally, when we have an array of element, we can form what is known as the partial sums. We have already seen that in the, so the sums of the form A1 plus A2, A1 plus A2 plus A3, all these partial sums of the form A1 plus A2, these n numbers you can call them as prefix sums, and there is a maximum among these n numbers. Let us say A1 plus A2 plus AQ is the maximum. Q is an index at which you have got the maximum. Finding this prefix sum max, we call it as prefix max. And we denote it by PM. Prefix max is PM. So, PM is maximum of all these numbers A1 plus A2, A1 plus A2 plus AN. Similarly, we can define suffix max. Or what is known as SM is maximum of AN. You come from the other end, from AN onwards, AN plus AN minus 1, AN plus AN minus 1 plus AN minus 2. And so on, finally AN plus these n numbers. Finding the maximum of all these things is also very easy. You start suffix max as, for example, AN, keep adding the value and updating the max. Okay, a one pass very simple algorithm. It is straightforward. Okay, it is very easy and straightforward to compute suffix max and prefix max in order n steps. Straight away you just keep, okay. Then we will introduce another quantity called block sum. Block sum for A1 dot n, this is called the block sum, is simply sigma I going from 1 to n of AI, sum of all elements in the array, that is called the block sum. Okay, for the entire block, the sum, that is called the block sum. Okay. Now, I am changing the specification in the following way. Input the array A1 dot n. Now, output maximum subarray sum, prefix max, suffix max, block sum. You can see that now I am demanding 3 additional stuffs. Earlier, for the given input there was an output, but in addition to that I am now demanding more to be given. So it is like for the given input I am now asking O x1 for the given input O x1 y1 z1 sorry O1 O2 x2 y2 and z2. Combining this I get O x y z. I have changed the specification to output more. You may intuitively think that even to compute MSS, if it is going to take n log n time, MSS and many more values are to be computed. Won't this take more time? Well, we are going to see that it is not going to take more time because they mutually help in computing in such a way that in order one step we will be able to get all those values. In other words, getting from O1 and O2, getting O was taking more time, but getting from O1 x1 y1 getting from O1 x1 y1 z1 O2 x2 y2 z2 O x y z is more efficient. We are going to see that. That is why we are going to get more for less. In other words, in our combining phase we are saving a lot of computations. Okay? So we will see how this is happening for our case. So here is the pseudocode and then we will see the justification. Maximum subarray sum A1 dot n. It is going to give 4 outputs. Maximum subarray sum, prefix max, suffix max and block sum. Okay? So it is going to give 4 outputs. If n equal to 1, when there is only one element, this is a base case, you do not divide, okay? Straight away you give the answer. Maximum subarray sum equal to prefix max equal to suffix max equal to block sum equal to A1. There is only one element, that is the prefix sum, that is the subarray sum, everything. So this is the and return MSS, PM, SM and block sum. Else let M equal to floor n by 2, make the first recursive call MSS A1 dot m. What are the outputs you are going to get? This is the first half. Maximum subarray sum 1, prefix max 1, suffix max 1 and block sum 1. All the elements A1 to AM added is in block sum 1 and the prefix max for this array, that is PM1. Okay. Second call, recursive call on the second half, A m plus 1 dot n, m s 2, prefix max 2 suffix max 2 block sum 2. So, the recursive calls have given 8 values. First recursive call has given 4 values, second recursive call has given another 4 values. Now, how are we going to compute these 4 values and return? So, this is where you can see how the logic works. The first thing is very simple. What is BS? BS is sum of all the elements. Sum of the elements from A1 to AM is available in BS1. Sum of all the elements from AM plus 1 to AN is available in BS2. What is block sum? Sum of all the elements from A1 to AN. Therefore, block sum is BS1 plus BS2. One is a subscript. Right? Block sum is sum of all the elements. Sum of all the elements from A1 to AM is available in BS1. Sum of all the elements from AM plus 1 to N is available in BS2. Recursive call return those values. Add these two, you are going to get BS. Now, let us look at the logic for prefix max. Okay. What is a prefix max? It is, you imagine this is 1, this is N, there is some Q, A1 plus up to AQ is the prefix max. This is the prefix max. So, there can be 2 cases. Q can be less than or equal to M or greater than M. If it is less than or equal to M, it is like this. This is M, your middle point, your Q is like this. Your Q is like this, case 1. The maximum is occurring in the first half. In this case, your PM is nothing but PM1. PM1 is the prefix max in this region. Prefix max in that region is obviously going to be the, if it is in the first half, that will be the maximum even in that subpart. Okay? It is a maximum over several other numbers. So obviously, it is maximum over this. Case 2, it is like this. This is position 1, this is M, your Q is like this, this is N. A1 plus AQ, which is a prefix max. In this case, from M plus 1, this is M plus 1. In this part, this must be the maximum. If this is not the maximum, if some other position is the maximum, then that would define the max there. So, therefore, this is nothing but prefix max 2. In the second half, this is the max, and all these numbers are adding up to block sum 1. Therefore, prefix max is block sum 1 plus prefix max 2 in this case. So, either this is the case or this is the case. If the prefix max position is in the first half, it is going to be like this. If it is in the second half, its value is all blocks added with the prefix max M2. Therefore, I can write the here prefix max equal to maximum of prefix max 1 or block sum 1 plus prefix max 2. Prefix max 1 a similar argument can be given for suffix max. What is a suffix max? It is like this: from n you have to add up to some index here, let us say some index r, up to this you have to add. So, there are two cases like this. It might be the r might be here, this is your middle point m. In this case, this will be suffix max 2, or it might be over here. In this case, it is suffix max here plus the block sum. So, case 1, Sm is suffix max 2 or Sm is block sum 2 plus suffix max 1, this part. Very similar to this argument. Okay? It is very similar to this argument. So, case 1 is suffix max or block sum plus suffix max 2. So, suffix max equal to maximum of Sm2 and block sum 2 plus suffix max 1. And what about overlapping max? And overlapping max is nothing but, if you look at overlapping max, okay, it should be maximum in this direction, it should, this is the point M, a segment that is overlapping M. This will be maximum if from M to the left it hits the maximum, and from right M plus 1 to the right it hits the maximum. This is P M2, this is S M1. Adding these two, SM1 plus PM2. All these values are available through recursive calls. Maximum subarray sum is maximum of MSS1, MSS2 and overlapping max. Now, return MSS, suffix max, prefix max and block sum. All of them are computed. Okay. Block sum is computed, prefix max is computed. So, you understand the logic for this is crucial, and this is another crucial thing. Recall that for finding the overlapping max, we have spent order and time, but overlapping max is computed in one step here, because this max is available for us by the recursive call. This value is also available for us as a returning value of the recursive calls. So, overlapping max took only order 1 time. Other computations are all order 1. In fact, if you look at block sum requires 1 addition, PM requires 1 addition, SM requires another addition, overlapping max requires 1 more addition. Therefore, this involves 4 additions. To compare maximum of 2 numbers, PM requires 1 comparison, SM requires 1 comparison, MSS requires 2 comparisons, 4 comparisons. So, in your conquering part, you have only 4 comparisons, 4 addition, which is order 1. Therefore, the recurrence equation is T of n is 2 times T of n by 2 plus order 1, because this is representing 4 additions. This is a combining cost and 4 comparisons. Anyway, it is order 1. So, you have 2 recursive calls made, 2 recursive calls made, and then you have done order 1 computation and solved the problem. That is why this is order n by master theorem. Now, you can see more for less. Getting MSS alone, obtaining only MSS took order n log n time, but obtaining MSS, prefix max, suffix max, block sum, they take only order n time. More for less, same idea. So, you have to be careful here. What are the additional things that will help to reduce the combining cost? If you mindlessly ask for more, it will act as an overhead. What we have seen is, in our n log n algorithm, the suffix finding and prefix max finding was taking order n time. If they can be returned as a values by the recursive call, we can simply use them and obtain overlapping max in order 1 time. That is what this improved algorithm has done. So, this improved algorithm is, it is the same algorithm except that we ask the recursive calls to return more values. If you want the recursive calls to return more values, then your original problem should also ask for more values. What more values it should ask? It depends on the problem. We have to be very careful. We can carefully look into the conquering part. We can find out what are the major values that require lot of computation. Can that be pushed into the recursive calls, and can we obtain them through recursion? If you could think that way, then you arrive at a more efficient algorithm. There is also a divide and conquer algorithm, and you can see it is asking more and achieving it in less time. So we are going to see more interesting examples of this kind. We will have a couple of more case studies where this more for less idea is so beautifully applied, and then a straightforward divide and conquer algorithm would be improved to a faster algorithm. Okay. Thank you.